Okay, so we'll kind of pick up where we left off. Um, so that quiz I posted after last class. So if we come down here, a little bit too far. So we've covered everything as of last Tuesday or last class that you would have needed to kind of answer any of those questions on that quiz. So I've got that set to be due at the end of the day, Monday. So kind of like the other quizzes, once you start, you have 60 minutes. It'll be everything that we've covered. You can kind of look at those practice problems as a way to kind of prepare for that. I also put up the complete version of problem set 3, so not just the first half. You've got 2 data sets that you're going to use. So the first half is using that first data set, and a completed version. The remaining questions are going to be using that second data set that I posted since the last class. So here's kind of where you'll submit that assignment. Once again, kind of submitting your do file. So we're down here today. We're going to use a lot of these files. I included an additional do file that I'm not sure how much time we'll be able to get to today, but I wanted to have it here just in case we have enough time to kind of dive into it. So the one that we'll be kind of starting with is that MLR week 6, and then week 6 and 7. That'll be kind of what we'll look at today, and then we'll spill over into next week. Okay. So a lot of that's just review of some concepts we talked about. We should talk about every single concept that you'll be tested on in the midterm after today's class. So next week will be kind of a little bit of review, looking at Stata a little bit, just to kind of give you some more assistance in completing that third problem set. It's due by the end of the day next Friday, right? And then pretty much once we do that, we'll be doing a lot of review for that exam Thursday, following Tuesday, and the exam is that following Thursday, March 5th, if I'm getting my dates correct, okay? So any questions from me before we kind of dive into things here? Okay. So we looked at this kind of traffic stop data last class. So I've got a bunch of slides, but we really looked at this in Stata. So this is just kind of some reference slides to go back to what we talked about at the end of last class. I've got a kind of blank slide in here, which I think we'll kind of get to eventually today, which is just an additional omitted variable bias question. So we already talked about this and how to calculate that bias, but I just want to show you a different way to do this in Stata. So we'll take a look at that a little bit later. So where we're going to start today instead is with imperfect multicollinearity. Okay? So we talked about last class perfect multicollinearity, which is what's one way I could get perfect multicollinearity by accidentally included the same variable, right? Those have to be perfectly correlated or perfectly multicollinear. We said we can also do this if we've got multiple dummy variables. So for instance, maybe on the problem set, I have one where you have to look at different income categories. If I have dummy variables for all of the potential income categories, if I include all of them in my regression, well, if I'm in one of them, I know all the other ones are going to be equal to 0. So we said we have to leave one of them out. Usually, which one do we try to leave out? The highest or the lowest. Okay, that kind of is usually what makes the most just sense in terms of portraying those results to a larger audience. So imperfect multicollinearity is going to be 2 variables that are highly linked, right? They're not perfectly linked, but highly linked, okay? So usually what that's going to do, if we include both of these variables that are imperfectly multicollinear, it's going to blow up the standard errors of one of our estimates. So we'll look at some examples today where we can kind of see this play out in the numbers. So what's going to happen is basically if I have these 2 variables that are somewhat collinear, but not perfectly, my first variable is a function of the second, right? So when I try to run these at the same time, it's almost like I'm throwing in the same variable into my regression twice, okay? Now, I'm not completely because there's still an intercept, right? And there's still some error term associated with that relationship between these 2 variables that are imperfectly multicollinear. But you can kind of think about it as a very similar issue as perfect multicollinearity. It's just not perfect, right? But it's pretty close. So here I'm going to use an example where I think about age and experience. Okay? So if I'm holding experience constant, as I get older, what is almost guaranteed that's happening to my experience on the job? So going up, right? As I get a year older, I'm going to have a year additional experience. Now, if I hold constant experience, everybody with 10 years of experience is not, for example, say 32. Some of them will be 32, some will be 34. But I know as they get 1 unit older, that experience variable will also go up by 1 unit. So they're not perfectly multicollinear because if I hold constant experience, age can still vary. So what we're going to do is take a look at this. So let's say I ran 2 separate regressions. One, I've included just experience, and experience and IQ. And I believe this was that wage data set we were looking at. So this is their impact on the Y variable of wage. Now, in a separate regression, I include IQ, but I also include just age. So when I run these separately, what's my rejection decision? Well, I might have moved my arrows a little bit too much here, but experience, p-value of 0.018, what levels could I reject the null at? That p-value is less than 0.1, 0.05, so reject at 95% confidence. Is it less than 0.01? Not quite, but still pretty highly significant. Now, my age variable, I have a p-value of 0, so I can reject that all levels. So it looks like both of these variables matter, right, when I'm predicting wage. The problem is, we've already talked about there's a link, or experience is a direct function of age, right? I can only get an additional year of experience if I'm also an additional year older. So what happens if I include both of these in the same regression, both age and experience? Well, I said, kind of alluded to what's going to happen, but we can kind of see it play out in a second. I said one of those variables, the standard errors are going to blow up, right? They're going to get very large. So before we kind of look at these results, if I do have 2 imperfectly multicollinear variables, right? So if I think about, maybe I'm predicting wage. I think I had as a control, what was it, IQ? And then I'm thinking about age, and I also include this imperfectly multicollinear variable of experience. One of these coefficients is going to have very large standard errors, okay? So if I think about, for example, let's say my prediction on experience. Okay? Well, when I'm calculating my test statistic for experience, what is that equal to? My coefficient estimate divided by the standard error for that variable. If my standard error, because of this imperfect multicollinearity, is going to be much higher, what's going to happen to my test statistic? My denominator is larger, my test statistic is going to go down. We think about how are we calculating p-values. I usually tend to draw this on the right, but it could be a negative coefficient. If I have a test statistic, what is the area to the right times 2? Because we always assume these coefficients are equal to 0. We always have a 2-tailed test. So this times 2 would represent my p-value. If my test statistic is going down, what's going to happen to my p-value? My p-value is going to go up, right? That area to the right times 2 is going to be larger. If my p-value is higher, is it going to be more or less likely that my p-value is less than alpha? Less likely, right? So when we run these imperfectly multicollinear variables at the same time, one of them, even though it looks like experience and age, and just intuitively should both probably impact my wages, right? I might be less likely to reject the null for one of them, well, even if they both matter. And that's because of that relationship between the two, okay? So any questions on this before we kind of look at the results? Huh? So if my test statistic is smaller, what's going to happen to the area to the right of it? It's going to get larger. So if my p-value is larger, is it more or less likely it's going to be less than alpha? Less likely. Right? If it's less likely, that means I won't reject. So even though I should be, I might fail to reject. I'll be making an incorrect rejection decision. So if I run these at the same time, Okay. And I kind of cut off some of this stuff just because it doesn't matter as much for what we're talking about. If I looked at age and experience, I can kind of see their coefficients. Now, when I ran them separately, what is going to be, if I leave out age, and it does matter, and it is correlated with experience, what's going to be true about this coefficient? It includes what? So if I leave something out of my regression that is correlated both my y variable and the variable I included, I'm going to have omitted variable bias. So my coefficient estimates, when I include age into that regression, they will change the coefficient size. Now, I don't know which direction unless I work out kind of what we did before to determine what that bias is going to be. Now, here we can kind of see when I included them at the same time, there must have been a pretty large positive bias in my experience variable, right? And that's because age is highly correlated with experience, but also correlated with wages, right? Typically, the older you get, you see your wages increase, maybe decrease, right? If you aren't keeping up with your skill set. I kind of think about this with like AI right now. If I get older and I don't update my skill set, I'm not as going to be useful as a worker if I don't have the use of these generative AI tools, right? So I said, what's going to happen if we have these imperfectly multilinear variables? One of them is going to have much larger standard errors. So if we look here, my standard error on this experience variable went from what, 2.9 to 3.35. So it increased that standard error. Now, it also decreased the coefficient. So when I calculate that test statistic, notice now, what is my p-value? Really high. So am I going to be able to reject the null that experience has no impact on wages? No. So if I fail to reject, what I'm really saying is there's no impact of experience on wages. Intuitively, we know that can't be the case, right? But the reason why is because this experience variable is so directly related or is a function of age that it's going to mess up our standard error estimates, okay? So here's kind of a nice example where it was really extreme, right? It increased my p-value a bunch. Right? Now, just to kind of reiterate some concepts, you can't see it here, but what value, if I fail to reject the null, what value is going to be in my confidence interval? 0, right? It's one of the potential values, right? So I failed to reject it, okay? Now you'll notice age is still highly statistically significant. So I'm still going to be able to, it only impacts one of these variables. Okay? Now, which one, it's a deeper concept, but for us, we're just going to say we don't know, right? We just know that it's going to impact the standard errors of one of our variables, okay? Any questions on this idea? Okay. So what are some solutions to this? Well, they're not great, right? So do nothing is the first one, right? We know one of them is going to be messed up. We just have to maybe think through this intuitive model that even though we fail to reject that experience has an impact on wages, we know that can't be the case. We just know that that's going to be an unreliable estimate, okay? Now, that's not a great, thing we can do. Now, if we have redundant variables where we think, okay, maybe it's not age and IQ, or sorry, age and experience. What if I included IQ and SAT scores? Well, those are going to be highly correlated, right? It's likely that your SAT score is a function of your IQ. So they're going to be imperfectly multicollinear. So what might we do? Well, we know they're both capturing the same thing, your underlying intellectual ability. So we would just leave one of them out, right? Now, hopefully that's the case. Here, experience and age weren't quite capturing the same thing, right? So if we do want to include both of them, what can we do? Well, what is going to impact my standard errors? So when we were thinking about that standard error calculation, all right, we had kind of this numerator and it was being divided by n minus 1. Right? So we're not going to worry about this for right now because what we're going to focus on is that impact of my sample size. So even if my standard errors are higher, what's one way I can deal with imperfect multicollinearity? If I increase my sample size, what happens to this fraction? Larger denominator decreases my standard errors. Everything works in reverse. I've now decreased my standard errors, I increase my test statistic, decrease my p-value, and I'm more likely to reject. So one way, if we know that two variables are perfectly multicollinear, if we can get more data or a higher sample size, we're less concerned about it. Because the higher the sample size, the more likely we'll still be able to reject the null. So in that earlier example, when the p-value went up to like 0.6, well, if I can get more data, increase my sample size, it's still going to be higher, but not near as much, right? By having a higher sample size, I can reduce that standard error, increase my test statistic, decrease that p-value. Okay. Any questions on that idea? So that's another solution. The fourth solution is I can transform these variables. So let's think about an example where, oh, I don't know. Let's say I want to predict, oh, what would be a good example here? So maybe I want to predict the number of individuals with a college degree in a country. I'm trying to predict that using the GDP of the country and the population. Well, what is true? If I'm thinking about the GDP, as my population goes up, what is likely to be happening to the GDP? If I just have more people, it's likely going to go up, right? So I know these two variables, one is a function of the other, right? Just holding all else constant, a higher population would lead to higher GPA values. So I know that I'm going to have this imperfect multicollinearity issue. So what can I do and still use both of those variables? Well, if I know that they both matter, right? Higher GDPs are likely that more people in the income, or sorry, more people in that country have higher income, higher availability to upper, higher levels of education. So it should increase the number of people with a college degree. But I also know if I just have more people, I'm likely going to have more people with a college degree. So I think these variables both matter. What I can do is transform these to create one variable. Now, usually this is a ratio, right? So what's something I could do with GDP and population? Create a new variable, which is GDP per person, right? Divide GDP by population. Now that should kind of be capturing both those variables' impact. It'll give me a slightly different interpretation on my coefficients, but it's still then being able to build in the impact of both variables without having this imperfect multicollinearity issue. In fact, you can kind of imagine, if I go back here, when we talked about this, if I take my first variable and I divide it by the second variable, right? Essentially, like I could rewrite x2 as a function of x1, and it kind of like cancels it out. That's, we don't have to go through the math, but that's the kind of intuition. All right. So that fourth solution is we can try to transform these variables. We'll take a look in Stata, like what this might look like. Okay. So let's do that right now. All right. So if I take a look here at this MLR kind of week 6. So this is where we'll scroll down. We looked at these examples, traffic stop data last class. We looked at perfect multicollinearity. So we're going to open up this kind of built-in data set. So this is where, if we're opening up Stata for the first time, actually, let's see, it might give me an error here. Okay, it didn't. I thought it would reset. It might for you, right? So if you haven't already, what is that? I think it's SSC install, right? We had to kind of upload those like free data sets. Right? So that kind of gives Stata access to all those data sets. Here, I think it's because I'm on my same faculty account. It already had it from the previous time, but this is where like my tech understanding of all the things at the university, I sometimes am not 100% sure what happens to like student user accounts. If for some reason you can't open that BQ Stata, you might have to run this SSC install command, right? That uploads all these free data sets behind the scenes. So add in that kind of line of code. Now we for sure can open up that data set called wage 2. So it has all these variables that we've now got in our data set. So let's say I want to look at, so we looked at perfect multicollinearity. These are just different examples. So I have kind of, if I run the same variable twice, oops, why didn't it like this? What do I have? Did I name this wrong? No, what variable was I? GPA. So maybe I was trying instead of GPA. Looks like I switched the example. Let's try to predict wages. We have the wage data set open, right? So if I try to kind of create a variable that is non-black based off of the individual being identified as black, these are going to be perfectly multicollinear. So if I create this variable, run my regression, it identifies that there was perfect multicollinearity, right? So when it drops that variable. So we're less concerned when we're actually using Stata about perfect multicollinearity because Stata identifies that and drops one of our variables, right? We looked at that last class when we were looking at like the traffic stop data and things like that. Now, what if we had imperfect multicollinearity? So this was my example of kind of using age and experience. So that's where we had one of those standard errors become a lot higher. So one thing that we could do as a solution to this is maybe I want to create this ratio of the number of years of experience I have to my age, right? So all I'm going to do there is generate a new variable, call this, I don't know, experience ratio. And I'm going to take the years of experience of the individual divided by their age. Right? Now I can essentially include both of those variables without including them individually, and I don't have to worry about this imperfect multicollinearity. Okay, so it's pretty easy to create these ratio variables and then kind of include them in my regression, right? And maybe here I can, who knows what's going to happen to this estimate, or who knows what's going to happen to its statistical significance. In this example, switches it to being not statistically significant. Okay, so it's not always a great solution, but it's one that we do have. Okay. Any questions on that? Because I know I added some stuff into that do file here. Okay. Sorry. Any questions on this? So, where are we at on time? Okay. So we're going to skip this additional omitted variable example for right now, I think just based off of what we've talked about. We'll return to this. I think we'll have time at the end of class. I'm going to hop into that new do file, which is week 6 and 7. Okay. Just going to show you a different example of imperfect multicollinearity, right? And kind of the different solutions we would have. So I don't think I have my global path in here. I kind of have it for you just in case you always going to have the same path set. So I'll make sure I open this up, and we're going to look at this QB salary data. Okay, so that's one of the data sets that we had on Stata. Okay? So I guess here I could do this for kind of the rest of class. Once again, if you ever forget your path, you can always open up the file, paste that file path, right? Now I kind of know where those files exist. Once again, for you, hopefully you're just dragging and dropping them in the same folder, so it makes it easy. I can open up, oops, I have an extra thing here on accident. I can open up that QB salary data. So this is quarterback salary data, and it's got a bunch of different metrics of quarterbacks, and I think it's the NFL, like NFL or NCAA. It doesn't really matter for the sake of what we're going to do. So here I'm going to kind of start out. I have this variable that measures the total value of that player's contract. So their salary, you can think of it as. I also have the number of completions that they had in that year. Okay. I also have the number of attempts. Right. So if I'm relying more on my quarterback, so he has more attempts, what would I likely expect for his total compensation to be? Higher. If he is more successful at those attempts, what would I expect his total salary to be? Higher. Right? You can put this in the context of any worker, right? If I'm relying on my worker to create more units, attempts should have higher total value or higher salary. If they are more likely to produce products that have no fault, not the faulty or the completions, it would impact their wage, increase their wage or increase their total value. So we can kind of take these sports examples, and they're really just different types of workers.
Is that like completion percentage or
just the number of completions, right? So you're kind of already thinking ahead, right? So if I run these two regressions where I only include these variables individually, what I'll see is, okay, the number of completions, not quite statistically significant, but pretty close, right? A p-value of 0.12. I'm almost can reject at that 90% level. Same kind of idea with the number of attempts. Pretty close, not quite statistically significant. Now, if I look at these regressions, what's one reason why those results, even though intuitively I think these should matter, why might I not be able to reject the null? Talked about it already. One solution I have to imperfect multicollinearity is if I increase my sample size, right, it decreases my standard errors. Or intuitively, the more data I have, my estimates are more likely to be accurate. So how many observations do I have here? 43, right? So a pretty low sample size in the context of like a lot of these data sets we're looking at. So our standard errors are just generally going to be higher, which is why even though we think these two things should likely have an impact, they don't quite hit our statistically significant kind of benchmark values, right? Not quite less than 0.1. So what can we do? Well, we kind of have a problem, right? Which is, scroll down an accent. We can't just get a higher sample size, right? This data doesn't. Now, if we could get more years of data and then run the same regressions, that would be a solution. But if we just have this data set and that's all we have, we can't really use solution 3. Solution 1 is always do nothing, so that's easy. I could just include one of them. That doesn't seem like the right thing to do in this example, right? Now, this is where they're imperfectly multicollinear, because in order to have an additional completion, what do I have to have? An additional attempt. But every quarterback that has 50 attempts doesn't necessarily have 45 completions, right? There's still variation, even holding constant that other variable. So what could I do? This is another great example where what might I want to create? Completion percentage, right? That would then capture the fact that I'm relying more on this quarterback, but also how successful are they when I'm relying on them more. So I could create a new variable, which is completion percentage, just divide the number of completions by the number of attempts. Now, when I include that variable only, I can include both variables, right? It's just that I kind of use them to create this new variable, but I'm not including them individually, so I don't have to worry about this imperfect multicollinearity. Now, if I run this regression, even with a small sample size, I have completion percentage is in fact statistically significant. And I'm capturing the effect of both attempts and completions by creating that ratio. Okay. Any questions on that idea before we keep moving here? Okay. Now, one thing that's just interesting to note, if I looked at just including my completions here, how much of the variation in the total value or the salary of that quarterback am I explaining? 5.6%. If I create this ratio, I'm essentially almost like including another variable. So what's going to happen to my R squared? It should increase. So if I come down here, when I've created that ratio variable and included it, what happened to my R squared? Went from like 5% to almost 9% here. So it did go up. So even though I'm creating this ratio and I really only have one variable on that right-hand side, because I use two variables to create it, it almost has the same impact if I just included both of them. So I can still get this higher adjusted R squared, even if I have to kind of deal with this imperfect multicollinearity issue by creating this new ratio variable. Okay. Any questions here before we keep moving? Okay. So let's go back at that do file. I'm going to save some of this. Well, we'll revisit kind of this here in a second. Kind of jump back to the slides. So we're going to revisit a concept we've already talked about. So these slides will probably look familiar because I've already used them. But I just want to remind us something that we had talked about. So we had not just the R squared, but we had the adjusted R squared, right? So we said the only difference between the R squared, which we can think of as the proportion of variation we can explain why, that's the same as 1 minus the proportion we can't explain. Now, if we're looking at the adjusted R squared, we took that proportion that we couldn't explain, and we scaled it by this factor that kind of captured the fact that if I increase my sample size, I always know that I can explain more, right? Now, I also know that if I add in more variables, I can also explain more, right? So this scaling factor kind of captured those two impacts. We talked about the effect of increasing the sample size. We also talked about the effect of including more additional variables, what that would have on my adjusted R squared. So we've kind of already discussed these things, but let's think about what their impact would be, okay? So if I simply add in more variables, we said, what's going to happen to my adjusted R squared? Assuming the sample size stays the same, K represented the number of variables we included on our right-hand side. So if I start to include more variables on my right-hand side, what happens to K? K goes up, right? So this is what I would do. Instead of trying to think through this, and you're going to have that formula sheet, so you're going to have in front of you my adjusted R squared is 1 minus that proportion I can't explain, multiplied by this scaling factor. I would draw arrows. I think that's the easiest way to think about this. So if I include more variables, well, I'm now subtracting a larger number. So what's going to happen to my denominator? If I subtract a larger number, it's going to go, man, I'm worried about the midterm. If I increase K, I'm subtracting a larger number, so this value would go down. If my denominator is smaller, this fraction is going to do what? Go up. If I'm now subtracting a larger value, what's going to happen to my adjusted R squared? It's going to go down. So this was the intuitive idea that as I add in more variables, I always know I can explain more of the variation. R squared has to go up. What the adjusted R squared does is it essentially captures how much of the variation is explained per variable. So it penalizes me for just adding in a bunch of additional variables if they're not really increasing that R squared by very much. Okay. So that was a concept we kind of talked about. We can kind of think about this adjusted R squared. It's going to be influenced by both that sample size and the number of variables we include. So we'll kind of take a look at this here in a second in Stata. And then we said as we increase n, that scaling factor gets closer to 1. So the adjusted R squared gets higher and higher or closer and closer to that R squared value, right? The closer this gets to 1, well, if this is 1, I've just got that equation, which is my original R squared, okay? So we also talked about how can I make predictions? And I think I revisited this last class with multiple linear, but before we go to Stata, just reminding us, let's say I'm trying to predict the wage. Someone has 105 IQ, 10 years of experience, and is 45 years old, okay? So if I looked at these regression results and I get rid of, this thing should go away here. There we go. How would I make that prediction? So if I'm trying to predict wage, I have this equation that I've run where wage is equal to the intercept plus the coefficient on IQ times this hypothetical person's IQ, plus the coefficient on age times the hypothetical person's age, plus the coefficient on experience times the hypothetical person's experience. So all I would do, it's basically just a linear equation. I take the constant, I add in the coefficient on experience of negative 1.43 times 10 years of experience. Add in the coefficient on age, 23.17 times their age. Coefficient on IQ times their IQ. So that's how we're making these predictions. We'll kind of see in Stata what's maybe an easier way of doing this than simply doing it by hand, right? So if I do it by hand, I've got rounding issues. It becomes a little bit trickier. Now in the quiz, you're going to have to kind of use, do it by hand. But there's a way we can do it in Stata that makes it a little bit easier, okay? So we can predict that dependent variable. When we're making these predictions, we said we're always going to be a little bit off, right? We have this line of best fit. Our prediction is always going to vary from the actual Y values. So how can I find those errors? We'll take a look at this. And I think I showed you a little bit last class, but I just want to review it again. And then we're also going to look at economic significance. So once again, this might look like a similar slide because we've already talked about this. But if I'm thinking about GDP, right, what's the effect of, 1% increase in the unemployment rate is going to have on my GDP, right? Well, if it does have an effect where it decreases GDP by 10 million, is that a large effect? kind of, but GDPs are like in trillion, I mean, right? Billions of dollars. So no, it's pretty small, right? So it seems large, right? The actual underlying Y variable is way larger than that. So it's a pretty small increase. So this is where we might want to scale some of our variables, right? We might want to scale GDP to represent thousands so that those coefficients start to look a little bit more readable, right? Because if the effect of 1% increase is relatively small, we're going to end up with things like 0.000001, right? So we might scale these up, and this was as simple as dividing GDP by 1,000, or dividing it by 1,000,000, right? And we talked about what should happen if I scale a variable. The coefficient will change because the underlying unit changes. But what should happen to the statistical significance? Everything stays the same. When we take that coefficient estimate divided by the standard error, the units cancel. So we should always find the same statistical significance even if we scale these variables. Now, what we haven't talked about yet, and I think I left this slide open, yeah. If I scale a variable, what's going to happen to the R squared? So I'm still using the same variable. It just has a different number of units, but is the R squared a unit? Is it a unit measure? It's unitless. So if I scale a variable, it shouldn't impact my R squared or my adjusted R squared at all. So we can kind of see whether or not this is the case. So we'll jump back into that kind of MLR week 6 and 7 do file. I'm going to look at this same kind of QB salary data. So we'll just leave off or pick up where we left off. So how could I make sure? One thing that we said is when we have this line of best fit, we're going to be making errors with our predictions. But on average, that error term should be 0. That's why it was the line of best fit. That on average, even though we were off by a little bit above or below for certain variables, when we thought about that scatter plot, the average error at every single X value should be 0. So we said, I think last class I showed you, you can, after you run a regression, so in case you didn't already, we run the regression with that ratio variable we created. Now, if I try to predict, right, the total value of this contract, so I call this predicted TV. You could call it predicted total value if you want to, I'm abbreviating here. Right? That predict command will use the coefficient estimates from the regression that you just ran. It will then, for every observation, come up with a predicted total value. So if I do this, it looks like it didn't do anything, but when I look at the data, I've created this new variable, which is that quarterback's predicted kind of salary or total value of their contract. Now, it's displayed weird because I have to move the decimal 7 places to the right. Contracts are usually in millions of dollars, right? So I've got the prediction, right? I also have, where is it at? The total value of the contract. So for each individual, what could I do? I could take that actual Y value. So that was what? Total value of the contract. Oops. Total value of the contract. Subtract that variable I created, which was the predicted. So all this is the actual Y value minus the predicted Y value. That should give me the error I was making for each observation. So if I do that, I'm going to have this new variable that's called error. Hopefully, when I summarize that error term, I should get an expected value of 0. Okay. So I'm going to kind of, did I create the variable already? I can't remember if I ran that code. Yeah, so I've got that error variable created. I'm going to summarize it, look at the output. Now it's a little bit off of 0 here, right? It's 0.11. Now, as I get larger and larger sample sizes, this should converge to 0. But for really small sample sizes like 43, it may be a little bit off, right? But remember, this, the salaries were in millions of dollars. My average error is 0.11, right? I'm pretty close to making errors of 0, right? Now, the higher the sample size we have to do this kind of thought experiment, it gets closer and closer to 0. The theory is that we would technically need to have an expected error of 0. Technically, I would need observations of infinite. Right? We can't do that, right? We can try to recreate this with data, but we don't have infinite sample size data sets, okay? So that's one way we could kind of come up with those predicted error terms. I also can use that predict command, create a new variable. Instead of making the predictions, if I put comma residual, residual is just a fancy word for the error I was making. So if I do this, it'll create a variable that is the error term, or the difference between the actual and the predicted y value. So hopefully if I create this, it should be the exact same as what I just did here, all right? So I'll go ahead and run that, and I can only run that after I've already run, it kind of always goes back to the regression, that previous regression I just looked at, okay? So if I look at the data now, hopefully when I created these variables, they're exactly the same, right? It's just two different ways of predicting the errors, right? Now, this took more lines of, a little bit more lines of code. So if we want to be efficient, right, this might be the better way to do it. Okay. But there's no right or wrong answer. It gave us the same predictions, right? Or the same kind of calculation of our error. Okay. Any questions on that idea before we keep? So once again, we're kind of revisiting concepts as we get closer to this midterm. I'm starting to build in, kind of going back, thinking about things we've talked about, also relating it to more of the current material, okay? So let's say instead, I want to go back and I want to open up a different data set, one of these free data sets. So I'm going to use this BQ smoke. We're going to open up this smoking data set, okay? So I'm going to try to predict the number of cigarettes someone uses based off of their education, pack of a cigarette price, for I think it's for a pack, whether or not they're identified as white, their age, and their income. Okay. So multiple linear regression. I'm going to run this kind of regression. All right. So I get all my coefficient estimates. What if I wanted to make a prediction? Well, I've now got like 5 variables. I'm gonna have to do this by hand. I have to worry about what I'm rounding my coefficients to. There's another way we can do this in Stata, and I think I showed you this already with simple linear regression. We can do the same thing with multiple linear regression. So what I'm going to do is I'm just going to use simply this display command. Okay. Now, if I run a regression, when I use this syntax of _b and then these kind of brackets, if I put the variable name in those brackets, what it will do is it'll take the coefficient from this regression for that variable. So if I'm making a prediction for cigarette use, I have to always make sure I add in the intercept of the constant. So I'll take that coefficient on the constant. I'll then add to that the coefficient on education for this hypothetical person who has 12 years of education. I then would add to that the coefficient on cigarette price times, well, what's the average price of a pack? Hypothetical value I gave you was 5. And then add to that the coefficient on white. Well, this individual is white, so that gets multiplied by 1. And then what's the predicted value for someone who's 30? Coefficient on age times 30. Income times 45,000. Okay. So if I use this display command, essentially the display command just does math for me. Right? It'll do whatever I put here and kind of show me the number. So I get a predicted kind of cigarette use, and I think this was like monthly, like 14 cigarettes. So this is nice instead of doing it by hand, because first of all, when Stata goes and pulls those coefficients, it's not rounding anything. It's taking, well, technically it's rounding. I forget what decimal it stops at, but it's like way, way out there, right? So I'm getting really accurate predictions. So I do this by hand, and I round my coefficients to the second decimal. I'm going to be off a little bit. All right. Now, when it comes to the quiz, or when we eventually get to the exam, if I ask you to make a prediction like this, you can't use Stata on the, on the exam. I'll tell you what levels to round those coefficients to. Usually, it's like round your coefficients to the third decimal, round your final answer to the second. That way, like, you're not going to be off by much, and as long as you kind of have your written work, I can tell like what you did was correct. But if we're doing this in Stata, we might as well be as accurate as possible so we can actually use those stored coefficient values from our above regression. Okay. Any questions on this? Okay, so I can do the exact same thing with a multiple linear regression as I was for that simple linear regression. I can use this predict command. I could come up with my predicted values for cigarette use, but I could also look at my predicted error term. We said I still use that predict command. This is what I want to call the variable. And then comma residuals just means give me the residuals or give me the error term, that difference between the actual and predicted Y values. So if I run this, what on average should my error term be? 0. So hopefully, if we do that, well, here I had a pretty large data set. I've got 800 instead of 43 observations. So this is one where theoretically we need an infinite number of observations, but the larger my sample size is, I can more like prove this to myself with data. So what is the average value of my error term here? Point negative value, that means move the decimal 9 places to the left. So 0.00000002, it's basically 0, right? So we can kind of prove these concepts to ourselves using data, especially when those sample sizes are high. Okay. I'm going to skip down here. I've got some things in here, but they're not as important for what we talked about today. So if I want to look at cigarette use, one thing that we notice, if I look at that income variable, which was just in dollars, what's the impact of having one more dollar of income going to be on almost everything? Really small, right? So let's say I want to scale this up, and maybe I want income to be represented in thousands, right? Because $1,000 increase there, I might be able to see it has a relatively large effect on things. So I'm going to come down here, and I'm just going to create this second variable called income2, where I've scaled the original income variable, but if I divide it by 1,000, the units is now thousands of dollars as opposed to $1. Okay, so I create this kind of scaled variable. I run that exact same regression, but I include the scaled version of income. So if before my coefficient was 0.0001, when I divide that income by 1,000, the effect is no longer an increase of $1, but an increase of 1,000. So what should happen to the size of my coefficient? It should go up. But if I know the effect of 1 unit, how could I get the effect of 1,000? Simply take that coefficient and multiply it by 1,000. So what should I get when I use my new scale variable? Instead of 0.001, I should get what? 0.1, right? So hopefully, when I run this regression, sure enough, I get 0.1, and then all the trailing decimals as well, but get the same value. Now, you'll notice when I scale one of the variables, I haven't changed any of the underlying data. All right, I've just scaled it. So what should happen to the coefficients and the statistical significance of every variable in this regression other than income? They should all stay the same. So if I go back up here, negative 0.37, negative 0.03, etc., I get the exact same estimates. And if I looked at those p-values, they're the same as well. Now, for the variable I scaled, that's where we get a different coefficient estimate because the units have now changed. But we said when we calculate a test statistic, I'm taking the coefficient dividing by the standard errors, which have the same number of units. So my test statistic and my p-value are unitless measures. So when I scale the variable, what should happen to that p-value? Stays the same. We can look at this, hopefully. Sure enough, 0.033, 0.033, right? So kind of revisiting these like scaling issues. Now, I also said earlier, if I scale a variable, I haven't changed the underlying data. So what proportion of the variation in wages should I be able to explain? Exactly the same amount, right? My R squared shouldn't change at all. I've included no additional variables. My sample size is the same. So what should happen to my adjusted R squared? Haven't changed N, haven't changed K. That scaling stays exactly the same. So hopefully, when I go back up to my earlier regression, right, 0.01, 0.0044, I get the exact same values. Okay. So scaling our variable, the only thing it impacts is what? The coefficient on that variable we scaled. Everything else in our regression will remain the same. And I should clarify, when I scale one of the independent variables, right? One of those X variables. Okay. Just as a thought experiment. Doesn't really make sense here, but we can do it just to make the point. Let's say I have this same, same regret. Oh my gosh, if I can type here. Same regression. It's not the best keyboard. And let's say, I don't know, for some reason, I want to scale my cigarette use by 10. I'm just choosing a range. I don't know why that means. Maybe there's like 10 cigarettes a pack or something like that, right? I don't smoke, so I don't really know. But, right, if I scale my dependent variable, so here let's think about if instead I scale my dependent variable, that y variable, what's going to change in this regression? So before we run this, let's think about it. So I had the original regression with the unscaled dependent variable. The effect of my coefficients are always the 1 unit change in the x variable on the predicted y value. So what's going to happen if I change that y variable, I change the units? Well, if 1 more year of education increased my cigarette use by 0.37, went down by 0.37, if instead that cigarette use is in tens, units 10, instead of going down by 0.37 cigarettes, it's going to go down by 0.0. So it's going to change my coefficient estimates, right? Because the change in my predicted y value now has a different underlying unit. But when I scale something, did I change any of the variation that exists in the actual data? No. So what should happen to my statistical significance for every variable? Exactly the same. What should happen to my R squared? Exactly the same. Hopefully I'm not lying to you. And when we run this regression, sure enough, right? Oh, no, what did I forget to do? I forgot to change this. At least now we have a good comparison, right? Because I have the other regression right before it. So if I use my new scale dependent variable, sure enough, what happened to every single coefficient? It was scaled by 10, right? What happened to my statistical significance? Exactly the same. What happened to my R squared and adjusted R squared? Exactly the same. Okay. So scaling variables doesn't matter. That's kind of the end result there. Okay. Any other questions on anything we kind of just talked about before we keep moving here? So I'll go back to this do file here. So we talked through this. We talked through the adjusted R squared. We use examples of this last class. What do I want to do today? I have 20 minutes left. So I'm going to be upfront with you. I don't want to rush through this joint hypothesis test stuff because it's kind of tricky and I want to spend a little more time on it. I believe the last question on the problem set was related to joint significance. So you should be able to work through the entire problem set except for the last question. We'll cover that last question on Tuesday. Okay. So you will have a little bit less time to work on that, but maybe on Tuesday's class, I might talk a little bit about the last question on that problem set to lead you to what may be the correct kind of way to approach it. And you still have a couple days to work on it, but I'll kind of give you some suggestions about, I might even pull up the problem set. Now for the quiz, has nothing on joint significance on it, so we don't have to worry the fact that we're not going to do it until Tuesday. Okay. Is that everyone clear on what I'm saying there? Okay. So instead of looking at joint kind of significance, I want to revisit something here in our data file. Okay. This is where I said to kind of do some extra work if we have some time. So I'm going to come down here and we're still looking at this cigarette use, but we talked about if I scale the variable, it doesn't change anything. So let's come down here and say, if I run a regression, and this is like the number of cigarette, I think this was like if the person worked in a restaurant. I don't know why that would matter, but let's just include it as one of the dependent or the independent variables. We have education, age, and income. Okay. I then want to include 2 additional variables. What should happen to my R squared? If I add in more variables, my R squared should always go up. Okay. So if I run these two regressions, and I know I'm reiterating a lot of these concepts, but just want to make sure we're getting it. Sure enough, what happens? Oh, my R squared values look the same. So if I gave you output like this, even though they look the same, that's only out to the what? Fourth decimal. If you add in variables, you know what has to happen to R squared. It has to increase. So even though you can't see it, if we could go out to like the sixth or seventh decimal, there will be a difference in the R squared, right? So this is where we're somewhat limited when we just look at the Stata output, because it's always going to have to round things. This is where we have to understand the concepts that even if I give you this regression output and you said, oh, the R squared is the exact same, we know it's not, right? We know that because that second regression added more variables, even though it looks the same to the fourth decimal, it's going to be a little bit higher. Now, this is where we can also kind of think about what variables did I add into this regression, kind of that white and cigarette price variables. So if the R squared barely went up, right? In fact, we can't even see to the fourth decimal that it did. What's likely to be true about the individual statistical significance of both those variables? If they barely increased R squared, are they good predictors of our Y variable? No. So what should be true likely about their individual statistical significance? Do they have a large impact on Y? No. So their p-value is going to be really high, or we're going to fail to reject that they have any influence on that Y variable. Sure enough, if we look at our regression results for that added variable of white and cigarette price, what happens to our p-values? They're 0.9. Are we anywhere close to being able to reject? No, which is why that R squared changed by so little, we couldn't even see it at the fourth decimal. Also, just a more interesting economic kind of thing here. If I hold constant all these other factors, so what is the interpretation of my cigarette price variable? If this is the price per pack, so if the price of a pack of cigarettes goes up by $1, the predicted use actually goes up by 0.004. Now that's holding everything else in my regression constant. Once we have multiple linear regression, I have to add that to my interpretation. That seems kind of weird. It goes against our law of demand, right? If the price goes up, people are actually buying more, holding all this constant. Well, what is the actual effect at all of our conventional statistically significant levels? If I fail to reject the null, I'm actually saying the effect is 0. So cigarette price has no impact on how many cigarettes people use. What does that tell you about what type of good cigarette taxes are? Going back to like introductory microeconomics here. If the amount I use is not impacted by the price, in fact, if it's not impacted at all, it'd be perfectly elastic. So like when we look at these goods, we can use this price kind of quantity data to get at a lot of these concepts we talk about in like our general econ courses. Right? So this is the value of what's supposed to be the value of this class, right? We can use data to actually then go out and test these different economic principles that we have. I was talking with someone the other day, because there's always this debate of like whether or not minimum wages have impacts on unemployment. And it's basically you can go out and get data and we kind of run these regressions and see like what actually happens, right? So I thought that was kind of an interesting example. I just wanted to point that out. Now, I have like a weird little example here where let's say I just run this regression. So I have the same regression output here, but I'm instead going to use a smaller sample size. So I would not expect you to do something like this, but essentially what this code will do, if I use a uniform distribution, this is just going to generate a variable, which is just random numbers. Okay? I'm then going to say, okay, if that random number, I'm going to sort it. If it's one of the 100 lowest random numbers, keep those observations. Or instead of dropping observation, we don't want to drop that. I'm just going to create this new variable called sample that's equal to 1 if that's one of the first 100 observations. So it should give me a completely random set of 100 observations from the original 800. So this is where we can start to think about. Excuse me. My adjusted R squared is this equation, right? If I instead limit my sample, right, what should happen to this scaling factor? So this is where it's a little bit tricky, right? If it were me, I would do this when I think about the sample size for an adjusted R squared. If the sample size was 3 and the number of variables I'm using is 1, what would this ratio be equal to? So if n was 3, k is equal to 1, I'd have what? 2 over 1. If instead I had a sample size of 100, what does this fraction become? 99 over 98. So as my sample size decreases, what's happening to that scaling factor? Oh, sorry, I'm going in the opposite order. Because, sorry, the example I showed you here, it's increasing. When we go back to Stata, I went from 800 to 100. So if n goes up, what's happening to my scaling factor? It's going down, getting closer to 1, right? If it's going down, when I subtract this value, my adjusted R squared should actually be going, if I'm subtracting a smaller value, it should be increasing. Now, in the data that we were looking at, I instead went to I'll do it in this color, smaller sample size. If my sample size goes down, what's happening to my scaling factor? It's going from almost 1 to 2. If my scaling factor goes up, I'm subtracting a larger value, so my adjusted R squared should go down. So when we run this kind of when I run that code in Stata, where I'm randomly selecting 100 out of those 800 observations, and then I run the same regression, but with that smaller sample size, what should happen to my adjusted R squared? It's going to go down. What's going to happen to my R squared? Theoretically, my R squared should stay the exact same, right? Now, it's going to be a little bit off because that's theoretical, right? We need infinite numbers of, we need large data sets here, but we can kind of see whether or not this kind of lines up with what our theory would predict. So I generate this kind of random number. I'm then just going to run this regression if that sample is part of that small sample size, okay? So we go here, run this regression. If I compare that to my old one with a higher sample size, we said what should happen to our R squared? Okay, well with these, it looks like it changes, right? But this is because I have relatively small data sets, right? So if I just randomly choose 100, maybe I happen to get the 100 observations that were a little bit better predictors, okay? Now, what's happened to my adjusted R squared is more what we want to focus on, that this little thought experiment can prove to ourselves. So if my adjusted R squared before was 0.01, we said with a smaller sample size, the adjusted R squared should go down even more. We're penalized for the fact that we found this observation from a small data set. So this is a really weird example where I was penalized so much that my adjusted R squared actually becomes, not only does it go down, it becomes negative. Is that actually possible if I'm thinking about the R squared? What's the lowest R squared could ever be? 0. But the adjusted R squared for small sample sizes, when I adjust using that scaling factor, sometimes it penalizes it so much. What is that really telling me? My model's not very good. Once I adjust for the number of observations, the number of variables I've included on the right-hand side, it basically isn't predicting anything, okay? So we know it's going to go down. This is a unique example where if that goes down by so much, it's less than 0, basically telling us our model's not that great, okay? Or at least given our sample size, our model's not that great, okay? I had kind of another like little thought experiment here where I would never expect you to do something like this, right? But I'm going to basically, there's a way in which just like you can make predictions and you can pull out the coefficients from a regression, you can also pull out that R squared value. So this is what that line of code does. So it's going to run this regression, save the R squared. It's then going to run this program where it randomly samples 100 observations, runs the regression, saves the R squared, generates another random sample of 100, runs the regression, saves the R squared. It's going to do that 100 times. So I'm going to have 100 different R squared values and kind of look and see what's the average. So I said before, it looked like my R squared went up, right, when I went to a smaller sample size, but that was only because I'm randomly sampling just 100. I only have one sample. If I keep making these random samples, on average, my R squared should be exactly the same as it was before. So if I go through, oops, I kind of run this regression. Oh, what didn't it like there? There we go. What did I do? Return scalar, non-R class, but not set R. Da, da, da. Why doesn't it like that? Well, doesn't really matter. We can come here, we can actually just look at the R squared, right? So it's 0.019. If I run this regression, oops, I do it 100 times. Takes a little bit to run this, right? Because it's doing it 100 different samples. But eventually, once it's done, I then summarize those R squared. What mean do I get? It's right around kind of 0.068, right? So it must be that if I'm kind of generating these random samples, right, of a size 100, because I'm doing it from a smaller sample size, those adjusted R squared values, right? Actually, what did I have here? Did I do this wrong? So I generated 100 times. I pulled out the, not adjusted, I pulled out the R squared. Did I run the same regression as I had up here? Why is that not giving me what I want? Shouldn't have an error here. So why is that? Looking at the right value. Maybe I'll save this example for next class. I must have an error in my code. R squared I. Okay, I'll pull this back in next class. I'll fix my error. But essentially what this thought, if you create this program, what it should do is generate like 1,000 different R squared values, and then the expected value of R squared should be whatever you ran from the original regression, right? And that's just because I'm taking a smaller sample size. I know my R squared should always be the same, okay? So we'll take a look at this kind of again next class. I'll update my code to make sure it's working. We can kind of revisit this. We really worked through everything except for this additional omitted variable example. So I think what I'm going to do on Tuesday's class is we'll first start covering this joint hypothesis test so I can kind of get that out of the way so that you've got that final question on the problem set. We'll then kind of revisit omitted variable bias just to, once again, start thinking about like reviewing for the exam. And then with that omitted variable bias, we'll kind of work through an example in Stata as well, just to kind of, I don't know, give us more practice looking at this output and thinking about how we can calculate omitted variable bias, maybe based off of me just giving you output from Stata, okay? So that should be everything we need, right? That's the only new material will be joint hypothesis testing on Tuesday. So we're already going to start jumping back into like things like omitted variable bias. We're going to start basically doing review, okay? And then Tuesday, I'll probably even pull up with the midterm practice. And Tuesday and Thursday of next week, we'll start working through some of those practice problems. And then we still have that Tuesday before the exam, which we're still just going to be working on practice problems. And they don't just have to be the practice problems I have. If you have questions, you can also ask them during those classes, okay? So if you've taken a look at that practice exam, feel free to bring in the questions that you have for those classes. Now, before I let you out of here, since you were here today, right, and this is where I need to make sure I get the time right so you guys can get this submitted. Whoops. So I'm going to change this. I think I've got it set to be 1:30. Let's do 2 o'clock. I'm going to save and publish this. So it should pop up on the main page. Oops, homepage. So we'll kind of scroll down here. That in-class quiz 5. So given kind of where we're at, we ran out of a little bit of time, but I wanted to kind of cover some of these things, and I'm not as concerned with these in-class questions. In fact, we'll likely use these in-class questions and revisit them on Tuesday for a little bit of review as well, okay? Now, the one that we talked about today was kind of if we have this imperfect multicollinearity, which of the following is going to be, oh, sorry, that would be high. I believe it's 91.80. Let me know if that's working. Yeah, okay. So my memory's not completely shot. We talked about imperfect multicollinearity, And really, what did we say that's going to do? It's going to make the standard error of one of those variables that are imperfectly multilinear higher. So we know that that answer is going to be when I run these imperfect multilinear examples or regressions, the standard error on one of those variables that is multilinear, one of their standard errors are going to be larger. Right? So that'll be kind of the answer to question 1. For question 2, I can kind of tell you the value. We haven't talked about this yet, but we're going to cover this on Tuesday. So how can I use stata output to actually calculate these test statistics for whether or not we had joint significance, right? So I'm giving you the answers today. This should be an easy one. I have the third question set to be 0 because I knew that we probably weren't going to be able to dive, even if we got to joint significance testing, we weren't going to be able to dive deep into it. So 0.67 standard errors on the cost per pack, or we don't know which variable it's going to be larger, but we know for one of them, those standard errors will be larger, right? So this is where these in-class attendance quizzes are really meant to be, like, for me, a way to kind of give you incentives, but also reward kind of class attendance. I think if you don't attend class, a lot of this stuff's going to be really hard, and I'm sure I'll kind of find a correlation with in-class quizzes and exam performance. We might even look at some of that data. I'll obviously strip the names, but like we could even look at that after the exam. So make sure you're getting those first 2 questions answered. The third one doesn't matter. It's not set for any points. Submit it kind of before you get out of here at 2 o'clock. And otherwise, I will have office hours on Monday and Wednesday. Those B251 students are still using them a lot. If you do want to meet on Friday, tomorrow, I potentially could have some time if you send me an email. So if you do want to meet tomorrow, send me an email and we can probably carve out some time for you to stop by. Otherwise, office hours next week as well. Okay? Have a fun, safe weekend. I will see you guys on Tuesday. I got a question for you.